Today, our speaker is Adam Reeve, and just to do a little family genealogy, he is grandson of Sally Cross, son of Polly and Brock, nephew of Bill, all of whom have spoken here. He is here today to talk to us about wind and solar energy, an industry he has worked in since 2013. He began his career in this field at DC Energy, an energy trading firm based outside of Washington, D.C., and he is currently a senior vice president at Surety in Boston, where he works on developing the next generation of financial and software products that enable risks within the renewable energy sector. He is a graduate of Yale, where he double majored in mechanical engineering and political science. Please welcome Adam Reeve.
Hi everyone, good afternoon. So first off, thanks for inviting me here. As I said, I'm grandson to Sally Cross here, and really excited to be here. So getting into things about me, as was mentioned, I currently work at Surety, which is a company based in Boston that does energy risk and data analytics. Before that, I was in Washington, D.C. doing trading in the wholesale energy markets. Before that, I was at Yale, but most importantly, I grew up less than a mile away from here. You may be able to recognize a photo of that house. That's not too far away, and so I'm familiar with Newbury Court and have been since an early age. So a couple of terms to get going. Let's poll the audience. Can anyone help me understanding the difference between weather and climate?
Weather is what happens today. Climate is what happens on the average over time.
Nailed it. So weather is the day-to-day. So these are warm-up questions. We'll get harder. So yeah, weather is the day-to-day state of the atmosphere, and climate is weather averaged over a very long time. And the reason that matters is the two are, believe it or not, often confused. My company spends a lot of time modeling both weather and climate, and climate change is talking about these long-term changes over time. So my next question is, what is climate change? Again, this is a softball, but looking for help.
It's pretty self-explanatory. I mean, it's the climate changing. Getting warmer in this case, but it's the climate changing, but it's probably much more technical.
Now you got it.
Over a period of time.
Yeah, changing over time. And in particular, when we're talking about it today and in general, it's usually the human-induced change in climate over time, right?
Oh, interesting.
Yeah, so climate definitely changes over time. It's warmer, it's colder over the span of tens of thousands of years. When we talk about climate change today, it's really the human activity that's causing that. So in particular, an increase in CO2 emissions that's causing the planet to be warmer than it otherwise would be. So why do we care about climate change? Well, this is actually pretty relevant. Earlier this week, a signatory, thanks to my mom for sending this news my way, 11,000 scientists basically signed a document saying climate change is happening faster than we expected and is going to have huge impacts on our ecosystems and around the world. So just quickly spinning through some of these different areas of impacts. Flooding, I think that people are fairly familiar with the impacts of flooding. Drought, conversely, actually is expected to happen more frequently as weather events become more extreme in general. Crop cycles will change, right? Seasonal patterns are going to shift as the summers become hotter and winters become shorter. We have also heat waves that will happen. So this past August, for example, in Texas was the second hottest August in the past 125 years. The hottest August in the past 125 years was in 2011. So the two hottest periods in the past 125 years both happened in this decade, and that's not a coincidence, right? There's a human-induced component here. Storm activity. So increased temperature in oceans means more energy in the atmosphere, typically leads to an expected higher intensity of storms. And lastly, we have sea level rise. There's two components to sea level rise. One is melting ice around the caps, but the other is just as water becomes warmer, it expands over time. And so even if we were to stop our emissions today, the fact that water is going to continue to warm over the next century or so means that sea level rise is going to continue. So these are meaningful impacts and hard to control for. And in addition, while there are expected to be changes in the long distant future, these are also ramifications today here. So this is a video. I'm going to see if I can get it to play. This is a satellite image of the coast of California. And these are the fires. This was taken last week. I was actually there and drove through some of this smoke. And it's pretty intense. We saw the fires from the highway. And it's amazing that this can be captured from space. So this is very real. It's happening now. Here is, let's see if I can go to the next slide. Here is way out in the future what might happen. An artist recently said what is expected to happen in the next century, the next 2 centuries, next 3 centuries. This is 2300, so way out in the future. But this would be the Charles River, Back Bay. You can see Cambridge across the other side there. If sea level rise continues as expected under the sort of no change of emission scenario. So having scared everyone appropriately.
Never been built on to begin with.
Yeah. So that's why we care about climate change, right? It's meaningful. Why is it happening? I'm not going to get into the science of that today, right? But I think that we're all generally familiar with the idea of greenhouse gas emissions, particularly carbon dioxide, that warm the atmosphere. Why are carbon dioxide emissions being released? Here's a graph that shows in 2018 the biggest sources of greenhouse gas emissions. Today we're going to be talking about that one that's highlighted in red. That's the electric power sector, right? So transportation is another big one. Those are the biggest two typically in the US. Sorry. Okay, so I'm going to get into now some of the energy technologies that are impactful in that electric sector. So first off, there's sort of 5 big technologies that generate electricity in the US: nuclear, wind, solar, natural gas, and coal. The 2 in the red, as you can see, are the most emitting technologies. So the y-axis here is carbon dioxide emissions by each fuel source. And coal is one of the earliest technologies that we've had in the US. It is by far the most emission heavy. Over the past several years, we've seen a big shift towards natural gas, which is great from an emission reduction perspective. It sounds ironic, right, that I'm excited about the concept of more natural gas plants, but if they displace coal, that's actually a very good thing for us. And so coal plants are closing at a record rate, which is a great thing, but there are still a lot of them in the US. The other technologies here, wind and solar, that's what I'm going to be talking more about today. Those emit no carbon dioxide as they generate energy, but there are, of course, costs in, say, building a wind turbine, right? You need to make the steel to build that. Or building a solar panel, you need glass and you need to mine elements. So there are emissions, but as you can see, far lower than traditional fossil fuel generators. Nuclear does not generate carbon dioxide, but there are a whole host of other issues with nuclear. So I'm not going to get into that today, but at a high level, I think it's worth mentioning. It's the most expensive technology out there. So happy to talk about that another time, but that's not the focus today.
I'm sorry, what is the most expensive technology?
Nuclear, yeah. So not many new nuclear plants are being built in the US as a result. So, exciting news for wind and solar is that while historically they've been very expensive relative to fossil fuel generators, that is no longer the case. So here we have, orange is solar, and blue is onshore wind, is the approximate cost of generating a unit of energy. Here, a unit of energy is a megawatt hour. For those not familiar with these terms, that's about the amount of energy to power 500 or so homes. And yeah, it is amazing. So solar in particular has really dropped in costs over the past decade, 2 decades. Since 1980, the cost of solar has fallen by over 99%, which is a phenomenal statistic. In the last decade, it's down 85%. Wind has fallen less, but is still cheaper, so is still a very cost competitive and actually more productive resource in the US overall. The gray bar there are the average power prices in the US. when the lines, so wind and solar cost of production, fall below that gray shaded area, that means that these technologies are now profitable, right? That investors are willing to invest in these because they'll make money. And so as you can sort of see in the past few years, we've crossed the point where they went from being, on average, unprofitable to being profitable, and that's a really exciting thing for the industry. And the good news is that's expected to continue. So here's a projection in the future, out to 2030. And each of the different 4 major technologies that I talked about earlier, coal, natural gas in black and green, and then solar and wind in orange and blue. This is the projected average cost of generating energy over this period. And as you can see, wind and solar are expected to be lower and stay lower than coal and natural gas over the next decade or so. So the good news is the momentum is really is there. These are expected to continue to be profitable, and we're really undergoing a revolution in the energy landscape at the moment. So an important question that I want to get into is why are we at this sort of inflection point? Why has the cost of energy changed so much for wind and solar? And it's interesting that it's really, there are 2 different reasons, one for wind and one for solar. On the wind side, it's been macro, it's been big. The solution has been for the wind industry to build bigger turbines, taller towers, and in so doing, gain a lot of efficiencies through that. And I'm going to get into the specifics there. For solar, these efficiencies have actually been on a smaller scale. It's by making solar panels more efficient, it's by getting materials more efficiently, and not necessarily just the efficiencies of scale that we're seeing on the wind side. I'll get into each of these technologies now. So first off, wind. I don't know how familiar everyone is with wind turbines. I was not familiar until 4 years ago or so.
Is that a wind turbine?
That is a wind turbine.
Because, I don't know, we have one in Holland.
Yeah, so there are a whole lot of actually different designs. Wind energy, utilizing wind energy for production it's thousands of years old. The old turbines do not look like we see today. As of, I'd say, about 15 or so years ago, the industry really coalesced around this single design of 3 blades, single monopole, it's called monopole into single tower. That wasn't always the case. So I was out in Palm Springs not too long ago, driving through where some of the oldest turbines in the country are installed, and you see turbines with 2 blades, or turbines with 4 blades, or 6 blades, sort of these exploratory experimental designs. That's no longer the case. These are sort of the industry standard, and the expectation is that they continue that way. So what's actually going on inside a wind turbine? Well, you can sort of think of it as a giant fan that's being turned in reverse, right? So wind is coming in the front, which turn the blades, those 3 blades, that spins the generator, which is mounted up on top of the tower in what's called a nacelle. Nacelle is the big bulb behind the rotor. That creates electricity, which goes out to the grid, which is fairly standard across all the different technologies out there. Now, how do the blades actually turn? Getting a little bit into the science here, but basically this is like an airplane wing that's attached to a giant rotating shaft. So if you look at the cross-section of one of these blades, it looks exactly like an airplane wing, where the wind flows over it and creates lift, and that lift rotates the turbine. In the same way that an airplane wing is used to create lift to lift the machine. It's the exact same concept. And to sort of illustrate that, because I think typically people think of fan blades which sort of push the air, right? Instead of create lift and actually are pulled through it. You can see a shot from below of a modern turbine that you can see that curvature. You can sort of imagine how if you attach this thing to the body of an airplane, that it could take off, right? It's the exact same design, and a lot of the same actually manufacturers make both. What you don't get from this picture is a sense of scale. Here's how big these things are. They're massive. So here's someone on the outside. Maintenance also happens on the inside of the blades, which scares me a little bit to think about. But they're really big, and I want to get a sense of scale. So the next couple of photos are sort of just for fun. But you can see how big these are. This is Jeff Bezos, the CEO of Amazon. I actually worked on this wind farm. Amazon and a bunch of other companies are doing a really great job in leading the U.S. industry towards buying more renewable energy. here is Mr. Bezos on top of a wind turbine that Amazon just bought, smashing a bottle of champagne on it. But what I like it because you can sort of see the scale as the camera zooms out.
How did he get up there?
I'll answer that in one sec.
Look at that, that's incredible.
No way.
Wow.
It's unbelievable. It's pretty impressive. How we got up there, so you can climb up inside the tower. Some of the modern ones have elevators inside, actually, just because they are so tall. These things are around 300 feet tall for the modern turbines. Oh, there we go. Okay, so here's, someone might ask, how do you make these things? I just think personally it's interesting as a mechanical engineer. Here's a photo of one being made. This is sort of half of the turbine. They're largely fiberglass resin, but you can sort of get a sense of the scale of someone inside it. So they're so big, the wing tip is moving at hundreds of miles an hour. The length, as I mentioned, is hundreds of feet long. And there are tons and tons of pressure. So from a distance, they sort of look like they're moving slowly, and they're these nice, pretty things. They're actually pretty impressive feats of engineering. So again, as I was talking about how efficiency is improved in the space, it's really through getting bigger on the wind side. So GE, General Electric, recently released the biggest turbine yet. And the CEO was actually in Boston this week to show it off at the Wind Testing Center in East Boston. And so I thought it might be relevant to mention that because it's a close to home example. Here you can see in blue the new turbine relative to other sort of world landmarks. And you can see that we're already getting up there to the Chrysler Building and the Eiffel Tower with the size of these turbines. They're really huge. This is a photo of a blade for this new turbine where it was manufactured. And it's sort of zoomed out, and from the back, I bet it's pretty hard to see, but each of those little dots on the ground is a person. And this blade is something like 220 people long, or they can stand next to each other. So it's really huge, and I think that getting a sense of scale is hopefully useful, because I often lose track of that when you see photos of them in the distance. Okay, so I've talked a lot about how big these things are. Why is bigger better? Well, there are three reasons for that. One is higher hub height, so bringing the nacelle higher means there's faster wind speed up there, and I'll talk about that in a second. The second is the bigger swept area, so the longer the blades are, is more wind is captured. And the third is that they're able to produce in a wider range of wind speeds. And I'll get quickly through each of these. So first, power output for the physicists among us. Power output is proportional to the swept area, which is sort of that circle there. You can imagine a circle that the blades cover. It's linearly proportional to that, and cubic, it's cubed related to the wind speed. So as the wind speed doubles, the energy that can be captured from it multiplies 8 times. So every little additional benefit in wind speed is meaningful in terms of power output. And so increasing the length of the blades, you can see obviously that that increases the swept area. But why does the height matter? Well, the height matters because wind speed increases with height. So in each of these curves is a relationship between wind speed on the x-axis and height on the y. And depending upon where you are, whether that's in a city on the left or an open land on the right, the relationship, how quickly wind speed increases with height, changes. But for the most part, you see that you're only at 75% of sort of the maximum wind speed when you're at, say, 80 meters or so. And as you increase the speed, increase the height of the turbines, you're able to capture faster and faster wind speed. And that matters a lot for making projects more efficient and therefore more economical. And then the last point I made was that bigger turbines are able to be used in a wider range of places. This is a map of the US color-coded by generation, so wind generation. If a wind turbine were built in every single county in the US, how much energy would it produce a year? As you can see, the sort of middle part of the US, the wind belt, as they call it, where it's very flat and winds can just sort of continue, a lot is produced. But on the East Coast, where we are, and places on the West Coast, there's really not that much production. Red is lower wind speeds and less energy. And as you get bigger turbines that are able to go higher up into the air and have bigger swept areas, you're able to make those projects that previously weren't economic actually good investments now. So not only are you able to make more money from the windy sites, you're able to expand the number of sites that you're able to actually build at, which is meaningful for the growth of the wind industry. Okay, so we talked about wind. What's going on with solar? Well, I mentioned before that solar is not driven by size. Solar panels are still about the same size they are today as they were 20 years ago. It's everything else that's been dropping. So here's a solar cost reduction breakdown. The red slice there, red outline slice, is the benefit associated with a bigger plant size, so with scale. That's about 10% of the overall benefit, which means that 90% is everything that's leading up to actually making the solar panels. So that's more efficient solar panels, that's reducing the cost of silicon, other materials, other components, the financing, all these different things add up and allow for cheaper solar projects to be built. Again, 99% drop since 1980 in cost, which is really incredible. That said, plants have changed with size as they become better investments. So here's a plant from 1988. You can see the little solar panels, the little blue rectangles there, as pretty small and separated areas, and it's a pretty small project overall. This is a modern project today, just orders of magnitude bigger. You can see how densely packed all the different panels are together, how much bigger they are. It's really become utility scale as investments have matured. And here's one that I really like. These are some Chinese solar projects. They're spending $3 billion on building solar projects in the shape of pandas, because that's what you can do when you have a government that just picks what they want to do. But I don't know, it's entertaining. Okay, so the good news is that because of these cost improvements and the fact that we're at this inflection point that I mentioned before, wind and solar have really been ramping up. Over the past really 10 to 15 years, we've seen us go from basically 0 installed generators in the US to meaningful amounts. That said, we're still in the single digits when it comes to comparing ourselves to traditional fossil fuel generators. So there's a long way to go. But despite this being great from an emissions perspective, they are intermittent, right? So I think this argument is one that's fairly common, which is saying, it's great that we can have wind producing. I think Donald Trump once said, "What happens if I want to watch TV while it's not windy?" That's I think a commonly held belief. I think it's a misheld belief. But the fact is they are intermittent, right? It's not, the solar panels aren't going to be producing much at night, and wind is intermittent. So I'm going to next talk about the impacts on electricity markets of these intermittent resources. Because now that the technology is there to make these efficient investments, it's a question of how do we integrate them with the rest of the supply. And it's a big question. Okay, so I'm going to be talking about what are power markets. Can I get a raise of hands? Has anyone heard of a power market or electricity wholesale market before? Okay, we've got a couple maybes. All right. That's totally fine. I'd never heard of it before I started my job trading in wholesale markets. So electricity is sort of split into two different components. On the top here, we have wholesale markets. That's where power plants are generating electricity and transmitting them hundreds of miles through high voltage transmission lines. This is where I spend my day every day on work. And where all of you and me in my life at home don't see it all. It's totally behind the scenes. What we see as consumers and end users is what's called the retail side of things. So after energy goes through the high voltage network, it goes through a transformer, and it goes through the local distribution network. Those are what we commonly see as sort of the phone poles around town. The wholesale grid is rarely noticed, right? So I don't really think about this at all, and I didn't even know it really existed until I started working in this industry. These are all the high voltage transmission lines around the US. They're everywhere, right? It's crazy. But we never really think about them because it doesn't impact our day-to-day. But it is impressive to me how large of a network this is. Okay, so historically, before early 2000s, all the different stages in this process were managed by utilities, vertically integrated utilities. So that meant that the utility owned the phone wires that bring you power to your home. The utility owned the transformer, which is sort of the intermediary step. The utility owned the high voltage transmission lines, and the utility owned the power plant. So basically they were, basically trying to deliver all of these components to you as effectively as possible, but it wasn't a competitive process. There was no competition between different utilities because they owned everything from the start to what you get in your house. So that changed. Starting in the early 2000s, power markets became deregulated. And so instead of having a single generator or utility in the upper left, we now have what are called independent power producers. So all these different people, if I wanted to start an energy company, I could start an energy company and try to sell my power into the wholesale grid. So could any of you. And what that meant is that these producers can compete with each other. And that's really changed the way that energy markets work. And as I'll get into that, as I'll mention in a little bit, it's meaningful because of how renewables are integrated. Okay, so we have a bunch of, in this new market structure, in the deregulated market structure, all these different independent power producers are able to generate power, and they bid their power into the market. So let's say that I was one of the generators up top. I could say, I'm willing to generate power for $10. And someone else could say, I'm willing to generate power for $15. What then happens is there's a central body that aggregates all these different bids and generates, if you remember your Econ 101, a supply curve. So that's down at the bottom here, where basically you order all the different bids and add them up, and you have a sort of willingness to generate curve. That supply curve is then matched with demand. So demand being total electricity consumption in the market at a given point in time. That's typically driven by how hot it is, say, so how much electricity people are using to power their air conditioners, their heaters, things like that. And the intersection of those 2 points, just zooming into that, would be the price of power at the given point of time. It's sort of economic supply and demand classic theory. Does anyone have questions on this? I realize this is going pretty fast and is new material, but if anyone has questions, happy to answer them. Yeah.
A little ways back in your lecture, can you use the land under these turbines for other things, or does it have to be dedicated area to those towers?
It's a good question. You can. And so in many cases, the turbines are built in sort of farming communities where it's very flat already. And so I often see photos of cows grazing underneath turbines or crops being harvested nearby. It's not designated areas. So it's open for commercial use.
Curious to know, I saw pictures of still poles with wires going across. Can you construct everything now so it goes underground, all electricity, or not?
The high voltage transmission lines that are sort of the wholesale level, all of those are up in the air. None of those are below ground, or very few of them are below ground.
Will they become more and more underground?
Maybe in the future. That's much more expensive, unfortunately, because you have to dig things up, and it's a harder process. So I would say unlikely. Yeah. So moving through this, we've now got a power price. Now, I think as we build this supply curve, on the bottom side, there is the lowest bidders. So that will be the wind and solar projects. Now, what's interesting, and this is really the challenge that my company is focused on, is what happens when there is no wind and solar. So when the wind slows down, or when a cloud passes over a solar plant, all of a sudden those bids disappear from the supply curve, right? So the supply curve effectively moves to the left, and the price of power increases dramatically. So we can sort of toggle between these two. You can see the wind and solar at the bottom side, and then it goes away and everything moves to the left, and the price has gone from $30 to $65. And that's a big change, right? If you're trying to build a project, it takes $100 million to build a modern wind farm, and if the price of power changes that much whenever you produce, that's a big risk. And so risks in the renewable energy space, the intermittency linked risks, is what my company is focused on, and they're growing as more and more of these renewables are integrated into the grid. And so that's sort of the big challenge that we're facing today. So with supply, as I mentioned, is sort of weather driven, right? As people use more air conditioners, more electricity is needed. That used to be totally fine for the electricity markets to meet that changing demand, right? Because they could just simply turn on the next power plant that was coal or natural gas because that was ready to go. The challenge now is that this generation side also is variable, right? So the wind changes minute to minute, the sun changes minute to minute, and so now you have this concept of net load, and that changes how power markets really operate. So this concept of net load is meaningful. Has anyone ever heard of the duck curve? The duck curve? It's basically this issue that, I'll skip ahead a little bit. I like it because of the graphic. But the idea is basically that as more and more solar is produced in the middle of the day, all of a sudden the net load, so consumption of electricity minus renewable production, is dipping down in the middle of the day. So here, the top line is from 2012. So this is California net load. In 2012, load was pretty constant across the day. As solar produces more and more, that pushes down the net load into the shape of a duck. And the reason that matters is, again, because of the intermittency linked component of this, right? If it's a sunny day, you get a very duckly shaped curve. But if it's not sunny, you end up with a pretty flat line, and that makes it really hard to manage production of power and electricity for generators in this space. So I'm wrapping up here, but what I wanted to basically introduce was the concept of renewables are this sort of inflection point where they're now profitable investments, and we're seeing a huge proliferation of them around the US and around the world. The challenge that they present, though, is the intermittency linked component of that production. Right now, there are two main areas where people are focused on solving that question. One is through physical solutions, so that's building out batteries on the massive scale. So Tesla, for example, is very focused on getting batteries deployed across the US and around the world. And there's also the financial solution side of things, and that's what I spend more of my time, but is managing the risks, the financial risks that companies are exposed to through this intermittency. So I think that the true solution is somewhere in the middle, is how do we combine the physical and the financial risk management tools to enable the growth of these technologies in the future. But the exciting thing is that they're here to stay. It's just a question of how do we address these challenges going forward. So that's all I've got, but happy to take any questions. Do you want to do?
Does the Yale School of Environmental Studies, are they doing much in this area too? Yeah.
Definitely, yeah.
How often or how much would be involved? Could you say?
Yeah, so in my time there, I took some classes at the School of, oh yeah, so I can, the question was, is the Yale School of Environmental Studies focused on these areas? And the answer is yes, definitely. It's climate change and energy markets are two of their primary focus areas. So I took some classes on that while I was there. Sure.
Your duck reminded me to worry about how the bird population does with these things. Are we just not supposed to care about that, or what's the story?
Yeah, yeah. So the bird issue, fortunately, that's been addressed the wind community is very focused on managing that. So a lot of projects that I've worked on have specific curtailment around bats. So bats do actually have a challenge with wind turbines. And so they actually shut down the whole plant when bats come nearby. And also have specific mandates around endangered species. So particular, like bald eagles, for example, they have mandates where if there's one in the area, they will shut down. Generally speaking, far fewer birds are actually killed by turbines than I think is commonly believed.
So shut down the whole field for one eagle passing by, do they?
They do, yeah. So in some cases they have systems that have either manual spotters. So they basically figured that it's cheaper to pay someone the whole year to stand there with binoculars and look for these endangered species. There are companies now that are trying to make that automated, to have cameras that look for special species. But yeah, they take it very seriously because it's a federal crime, and then they lose their generating permit.
Good for you.
Excuse me. My question is there enough land in the United States to build these wind turbines that would provide some electricity? I mean, obviously, we're not going to provide all of our power through wind turbines. I mean, there's going to be solar, there's going to be, I hope there's not going to be nuclear, but
Right.
anyway, is there enough land to build these wind turbines?
Yes. So good question. There is enough land, and so between wind and solar, certainly. And the exciting thing, I think, about wind in particular is that it actually takes up very little land space because, as I mentioned, that it can still be used for farming around it. Under construction, you definitely have to clear the way, but then once it's back in operation, you can completely use that land around it. In addition, there's offshore. So Massachusetts is actually one of the leading states in terms of developing offshore wind. And New York, New Jersey, that's sort of the next era as well. I didn't mention it here, but there's a big opportunity there as well.
Some of the early wind turbines were destroyed by vibrations created by wind shear. Is there any risk that these huge wind blades that haven't been run many years may fatigue with time and suffer the fate that some early wind turbines? Are you sure that the life expectancy is what you think it is?
I don't think we'll actually have an answer for that until they run for a few years, right? Until we can see it out. I know the testing has become more exhaustive as the industry has matured. So there's a wind testing facility, as I mentioned, in East Boston, that is more rigorous testing of modern-sized blades. I don't know about the old blades and how they were tested, but I think as sort of the focus on performance and efficiency grows, the testing has become more thorough, but only time will tell ultimately.
I was wondering about China. They have a lot of land, and apparently they're doing big things with wind.
100%, yeah. So China is the world's largest installer of wind and solar. They've really made it a priority, which is great to see, given how historically there have been challenges with pollution there and very coal-focused.
Regarding birds, Audubon has studied to kill birds with turbines, does not feel it's a consideration that we really need to worry about. If you're worried about birds being killed, keep your cat indoors. They kill far more than wind turbines.
I have a question. Did you prepare all these slides?
Yes.
Oh my gosh, that's impressive. You're really wonderful.
Can you bring us up to date on superconductors and whether there's any important science that they can transmit this energy over longer distances at less cost?
I could try. I don't know the latest on superconductors. There is a big effort to do long distance, high voltage DC transmission, not necessarily superconductors, where they basically would build these long transmission lines from windy areas, so Oklahoma, for example, to Arkansas and other places where simply it's not as windy, and so the price of power is higher. So that is a major effort. The challenge there is getting the permitting to build towers. It is above ground, or even if it's below ground, getting the permitting to build that multiple 100-mile line. Can't speak to superconductor specifics, unfortunately.
Given what you do, you've not surprisingly been focusing on the supply side. But I was struck by the steepness of that demand curve. It's very inelastic. I mean, apparently the price could vary hugely and demand doesn't change much. Why?
It's a great question, yeah. So I guess, I don't know if anyone here, but I certainly haven't been aware of the price of energy in a given hour and adjusted my behavior accordingly, right? You don't know that the price of power is $1,000, so I'm gonna turn down my air conditioning, right? That's just not something that we have the information to act on right now. In addition, there simply isn't the motivation, given how retail structures typically are. When you pay your electricity bill, it's often a fixed rate for multiple years into the future, or very, very little variability. And that's because your retail provider has locked in a price from someone else, so they sort of hedge their risks. And so what that comes down to is there isn't really either the motivation or the information to enable a demand curve to be elastic. There's some great companies out there doing really smart work, including in Boston, that focus on making that more elastic, particularly for huge consumers. So if you're running a warehouse or a grain elevator or some big consumer of power, you care about what the price of power is in that hour, right? But getting them the information so that they can act accordingly has been a challenge, but fortunately, we're definitely headed in a smart direction there.
How are the oil companies addressing this competitive threat?
Good question. In two ways, I think. One is lobbying for more subsidies. So coal and nuclear actually have gotten significant subsidies in many of the Midwestern states. Ohio just passed a major series of regulations that subsidized coal and nuclear, which is frustrating to see. But there is the other side of the coin as well. So Shell New Energies is one of the major investors in the Mayflower Wind Project, which is off Massachusetts coast. It's about 20 miles south of Martha's Vineyard. And they are a leader in what I'm pretty excited to see as sort of companies that have an established energy presence and are pivoting towards what they see as the new future. Not everyone's doing that, unfortunately.
Hi, one historical comment and then a question. The Dutch have been using wind power for generations to pump water. The other question I have is, what is the role of solar panels on houses?
So solar panels on houses, that's a good question. That's not, a lot of what I talked about here is called utility scale. So those are huge projects that are managed by big developers. Solar panels on houses would be called distributed generation, right, where it's scattered around the grid, or residential scale solar. And those are growing rapidly. So in California, for example, a huge percentage of solar generation actually comes from the distributed generation. It is more expensive, so it's about twice the cost, just because instead of assembling 2,000 panels, you are assembling 2 panels, but you still need to install the same connection equipment and stuff like that. So it is more expensive, but it's meaningful, and actually in Massachusetts has a pretty significant portion of energy coming from that as well. So it's growing.
Most of your stuff is refer to the United States and the Western world. India is building a couple of coal-fired generator plants a month, projected out many years. How are we going to touch that?
I don't know if I have a great answer to that, unfortunately. Yeah, the impact of building different sources of energy. So in areas where, in places where thermal energy is still more cost effective, so in some places that's China, in some places that's India, they sort of respond to UN motions towards pushing towards clean energy, saying basically, United States, developed world, you guys have been polluters for decades. It's our turn, and we need this sort of, the cost effectiveness of these dirty technologies, and that is a hard dialogue for sure. So I unfortunately don't have an answer. I think that international cooperation is critical to that. U.S. I don't think is leading the way right now, but hopefully that can change.
The other component to make wind and solar really practical is energy storage, and there's a lot of work being done on batteries. What's your take on the outlook for battery storage?
Very optimistic. So that would fall on the physical solution side here, right? So as intermittency increases, the ability to store and basically weather through the variability of the solar and wind production matters more and more. And so battery costs are falling by a tremendous amount year over year, something like 9% per year for each of the past dozen years. And so that definitely is sort of the future, is on the storage side. I think storage and transmission are viewed primarily as the two main solutions on the physical side for solving intermittency, is either being able to store the energy where it's generated until it's needed, or transmit it from one area to another, where there'll always be some place where it's windy. So those are the two ways it's being approached right now.
The smart meters will also help with that, which California is a leader in, that will, when we get smart, we're gonna use our electricity at night when it's cheaper to generate, or when there's an excess of it, and your curve is now makes it economical to run things in the evenings when the electricity is cheaper. And that will be the same kind of thing as battery storage. And certainly you didn't mention pump storage, which has been available for decades and decades.
Yeah, so pump storage, I can touch on that briefly. That is huge. That is the biggest single source of storage right now in the US. I interned for a couple summers at a hydro turbine manufacturing group, and we focused on one of our areas was pump storage. And yeah, I agree that is big. The challenge with that, so for those not familiar, pump storage is basically pumping water up a hill into a reservoir when electricity is cheap. And then when electricity is more expensive, letting it come back down and spin a turbine, and then selling the energy that's generated through that. So it's like a physical battery using gravitational energy to store the energy there. And it's a very old technology. It's a very efficient technology, but there are very few places in the US where you can use it, because you need a hill that's big enough, and you need a source of water, and the two aren't always, and you need a place to store it at the top of the hill. So it's, unfortunately, the scale of that, I think, is limited. And then the second part is smart meters. That's called load shifting, is where basically you incentivize people to use, say, their dishwasher or their washing machine at night instead of the day. Texas is doing a great job with that right now, where they send phones texts if the prices are high and say, the prices are really high today because it's really hot, so people are running their ACs. We will discount you energy use tonight, for example. So they are starting to reduce that information gap that's needed to make the supply-demand curve more elastic.
One point in a question, it ends up that in wintertime, the wind is higher, and in summertime, the solar is higher, so they complement each other seasonally. The question is, what areas or geographic countries are requiring solar as a code to be on houses being built?
Sorry, the question is which parts of the country?
Well, I know Germany requires solar-run homes being built. In any places in the States that's being required now?
Yeah, California does right now. So for those who can hear, the question is what areas require new homes require solar to be built. California recently passed some legislation last year that requires all new homes to have solar panels on their roofs.
I was wondering about the cost of electricity. Is it going to keep going up and up and up?
I'll just that in 1 second. I think there's a question on the microphone back there.
Your four major sources did not include either water, hydroelectric, or oil. Can oil be used to produce electricity?
Yes. So hydropower, water, is actually, and has been historically, the largest renewable energy source in the U.S. It is the single largest producing or largest use source of energy for other major countries. Brazil, for example, something like 95% hydro. Canada, particularly on the West Coast, is very hydro-driven, as is Washington, Oregon, parts of the country. where you have big elevation changes and a lot of precipitation. Unfortunately, or for better or for worse, that's not viewed as an infinitely sustainable technology. There are major impacts on rivers that make it questionable from a long-term sustainability perspective. So that's generally been there hasn't been much growth there in recent years. On oil that is commonly used, that is much more expensive. So that's used in New England when not enough natural gas can get here, which does happen during cold snaps in the winter. It's been historically the primary fuel source in Hawaii because you can import it on a ship. But it is very expensive and very polluting. And it's only a small single-digit percentage of total US energy use. So that's why I didn't focus on it.
How about the government? Are we involved in, because our president doesn't believe in these things, what is your connection with the government as far as development?
I am not personally connected with the government. It's been frustrating, for sure. It's been a challenging environment to work in. I think on the federal level, I think what's been pretty impressive has been the smaller government reaction to the federal government inaction. So on the state level, on the city level, on the large corporation level, there have actually been a number of players that have basically said, we are going to stick to the Paris Accord, which is agreement on how to address climate change and greenhouse gas emissions, regardless of what our president and our federal policy is. And so that's been exciting to see, but obviously I'm hoping for a new direction next time around. We had one question here.
The cost of electricity, it's gone up tremendously in the last couple of years.
Wait, don't speak out without the microphone. Here it comes.
Thank you. I was wondering about the cost of electricity because it's gone up so much in the last couple of years. Is it going to keep going up and up and up? And what is the answer to that?
Yeah, so the question about electricity going up and up over the past few years, I think that there are two different prices that are important to keep in mind on the electricity landscape. And actually that was, well, I can flip through far enough, but that's wholesale and retail. So interestingly, the cost of wholesale power has actually declined significantly over the past few years. And that's primarily a function of two things. One, natural gas being cheaper. So the U.S. has transitioned from a country that didn't produce much natural gas to being the largest producer in the world. And that's through technology fracking, which is controversial in its own right, but that has had an impact on the industry. And the other are renewables. Renewables are so cheap, as I mentioned now, that's brought down the cost of electricity. What has become more expensive is the transition to the retail side of things. And that's for a number of reasons. In some cases, it's paying for subsidies. In some cases, it is locking in long-term rates that sort of get expensive through other ways. In some cases, it's PG&E, for example, in California just went bankrupt, and so that's on ratepayers to manage that. There are a lot of reasons why the retail rate may diverge from the wholesale rate. I spend most of my time on the wholesale side, so I can't speak to why prices have increased here.
With respect to physical solution, large-scale battery storage is not going to work. With lithium-ion batteries at 200 megawatt storage explode and get fired because of the heat dissipation problem. So there is no real solution for large-scale grid-sized storage except hydro.
I'm not a battery expert, so I'm not going to argue with you on that. I think that there have been some examples recently of successful large-scale batteries. Depends how large we're talking, of course. Yeah, so maybe it's a 200 megawatt ceiling. In Australia,
I'm familiar with that.
well, yeah, so for those not familiar, Australia recently, the largest battery in the world was built there by Tesla, so Elon Musk doing his thing. And the Australian power market is extremely volatile. because of renewables, as I mentioned here, it's sort of this scenario, this intermittency risk on steroids. And so the battery helped quite a bit in that scenario, but there may be physical limitations on the maximum size that I'm not familiar with, certainly. Yeah.
What are the economics for a big power company that has installed, let's say, oil, or not oil, but coal and gas plants, to install solar and to shift over?
What are the incentives? Is that the question?
Yeah.
Or the economics?
What are the incentives for them to make a change so that they can distribute cheaper electricity to their area? I'm thinking of a project that's going on, you're probably familiar with Duke Power down in the Carolinas is engaged in a project to install major solar power. And that will presumably replace existing plants, which might or might not be fully depreciated. But what's their incentive for doing something like that?
Yeah, so I think that there are two motivators that would push a large generator company, right, to transition from traditional fossil fuels to renewables. And I've actually worked with Duke on a couple of projects. One, I think, is just pure return on investment, right? So as I mentioned earlier, wind and solar are now actually cheaper than traditional fossil fuels on an expected return basis. So if your job is to make a 9% return for your investors, solar and wind are actually good vehicles for that today. The second is that there's a big movement, and we're seeing this across many parts of the industry, is really towards stakeholder interest in ESG, so focus on basically sustainability, that increasingly companies that don't take sustainability seriously have problems or have pushback from their board and from shareholders. And so that was, there are lawsuits, for example, going on where I think it was ExxonMobil was being sued for not disclosing knowledge about sensitivity to climate change to their shareholders. So there's an increased sort of sensitivity and awareness to that. And so I'm hoping it's not just for optics that they're building out these new projects, but I think that certainly is a motivator.
Thank you.
Thanks, everyone.
Oh.